afternoon is Nikolas Kyriakopoulos from University of Toronto. Get it close, right?
Not bad, not bad. All right, we made it. The last presentation of the day. My name is Nick Kyriakopoulos. I just finished my master's at the University of Toronto under Professor Christopoulos. I'm now in consulting. And my presentation is entitled The Upgrade of Seismically Deficient Steel Frame Structures Built in Canada between the 1960s and 1980s using Passive Supplemental Damping. So I'm just going to give you a really brief overview of the background of the project and the project objectives. Then I'm going to identify to you the CSRN benchmark steel MRF hospital structure. I'll then go into just a little bit of my experimental program that assessed some connection behaviors, followed by the nonlinear modeling of representative frames. I'll then show you the performance spectra-based design approach and how this can be used to design passive supplemental damping retrofits. And finally, I will conclude. So partially restrained connections have been used since around the early 20th century in steel moment frame construction. These connections were primarily designed for moments caused by wind loading only, and they were actually allowed to yield under gravity loads. And this provides some inherent ductility because the top and bottom cover plates, as you can see here on the beam, they were designed such that they could develop their full axial yield force. These connections were said to have, they were designed such that they had adequate rotational capacity, but there weren't really any hard limits on what this was. And the beams were actually designed as simply supported and were designed for gravity loads only. One incarnation of the partially restrained connections in Canada was the Type 2 construction building philosophy in the MBCC 1965. And some current research has suggested that these systems are more ductile than we might give them credit for, and that they have almost a century of successful history to point to. Now these are different than the pre-qualified connections that famously displayed the brittle fractures in Northridge and Kobe, as those were seismically designed, and they primarily had the beam flanges connecting directly to the column, whereas these have the cover plates. The SAC project did address these briefly, but not nearly to the same extent as the pre-qualified pre-Northridge connections, and they said that more work was required. So my project objectives were to identify a generic non-seismically designed building type in Canada between the 1960s and 1980s, which was identified as a little bit of a boom period in steel construction in Canada, and that is that Type 2 construction that I was talking about. Then examine typical connections from a typical Type 2 construction building type found in Canada, and address some interstory drift limits. Use nonlinear models with strength degradation considerations to assess the seismic behavior of the structure. And then finally propose retrofits using a performance-based design methodology using passive supplemental damping without the need for local connection interventions. So this is the CSRN benchmark steel MRF hospital structure. It is located in the Quebec City region, and it is 34 meters of glorious Type 2 construction steel MRFs. There's 3 bay frames in the short direction and 7 bay frames in the long direction. And it sits on top of a concrete podium that was completely ignored in the analysis and was soon to be perfectly rigid. A 3D model in SAP was performed just to do a quick modal analysis, and in addition, representative frames from both orthogonal directions were also modeled, and it was found that this building had minimal torsional effects and is fairly regular. I previously mentioned that Type 2 construction was designed for wind loading only in the lateral direction, so therefore this structure right here could have been built anywhere in Canada that had similar wind loading, independent of what seismic hazard it was. So using the MBCC 1965 climatic data tables, it was found that Montreal had comparable wind loading to Quebec City, but in addition, Vancouver had similar wind loading to Montreal. So this study is going to analyze the structure as if it were built in both Montreal and Vancouver. A site visit was performed, and these top 3 pictures are from the short direction in the 3 bays, and then these bottom 3 pictures are from the long direction with the 7 bays. Now, this is showing connections framing into the weak axis of the columns, and this is showing the connections framing into the strong axis. They both have bolted shear tabs that are welded to the column. Both have welded top and bottom cover plates. the top three pictures, you'll notice that there's a CJP weld connecting the top plate to the column with a backing bar. And this top plate was either bent or inclined to accommodate the geometry of the backing bar. And then in this direction, we determined that there was a misalignment. And the construction drawings showed that the beam flange was supposed to be flush with the continuity plate, but this was not the case. And these top plates were also either bent or inclined. The detail connecting the top cover plate to the continuity plate, we really couldn't get at that, so this was inferred at a later date. This is half of the 3-bay frame, and this is half of the 7-bay frame, to give you an idea of what they look like. We did a spectral analysis for both Montreal and Vancouver, and we wanted to get an idea just of what we're looking at. So one of the things we did is we used the displaced shape from the spectral analysis to calculate the U2 factor to determine how important are these P delta effects. One thing to note is that the base columns were actually pinned. They were pinned to the concrete podium. So the frame 6M, the far one there, we determined actually that the first 4 floors plus the 7th exceeded the 1.4 limit for the U2 factor. And this 3-bay frame, this first story also exceeded the U2 factor. The limit, that is. So therefore, this indicates that the building is very P delta sensitive. We could probably expect a soft first story, and this will likely lead to global instabilities. So then an experimental program was conducted using the reverse cyclic SAC connection protocol. This was done to observe the cyclic response and identify the failure mechanisms of the connections. We also wanted to determine their initial stiffness. We wanted to see the yield moment, maximum moment, and ultimate moment of the connections, as well as the rotations associated with those levels. This was the experimental setup. This was at the University of Toronto. We had a concrete strong wall, 2 1,000 kilonewton actuators that were pushing off the strong wall that were attached to an outer racking frame. And this outer racking frame had 4 true pins in it, so it provided next to no lateral resistance. And inside of that was my H-shaped specimen. I had 2 of them, 1 for each direction. And so because it's an H-shaped, I actually had 2 connections per specimen for 4 connections in total. And this is what it looked like for the first test as it was constructed in the lab. So these are just some pictures of the failure mode. So this is the first test, 1 connection for the first test. We had yielding of the plate in tension and then buckling of the plate in compression. And at higher rotation, we found some weld zipping. This was followed by, once the top plate kind of lost some of its strength there, the shear tab and the beam at the column, the beam web that is, they started to yield and buckle a little bit. And then we had a brittle CJP weld failure, right where the top plate connects to the column. And then at the end, the force couple, since the top plate was basically out of the equation, the force couple was between the shear tab and the bottom cover plate, and this led to either shear tab ripping in tension or severe buckling in compression. The frame 6M connection was sort of similar in some ways in the sense that we had plate buckling and compression. We also had weld zipping. But then we had a plate failure, and in fact, we actually had beam bearing. The edge of the beam in this direction, the detail was closer to the column, and so actually the top flange of the beam was bearing onto the continuity plate, and this caused a very large uptick in force. And actually, we cycled these connections. We did 2 full 5% inter-story drift cycles, and we couldn't degrade this connection any further, so we just kind of called it quits there. This table summarizes the connection behaviors and damage levels associated with various inter-story drift levels. What I want you to get out of this, though, is that we actually had some pretty good connection strength up until 2% inter-story drift. That's kind of when the strength degradation occurred. So that's a fairly good limit, because if you consider that the MVCC limits the inter-story drift for critical infrastructure to 1%, this means that these connections can handle this. Also consider that pre-Northridge, pre-qualified connections, they yielded and sometimes actually fractured before they were able to yield at around 0.75% to 1% drift. So these connections, even though they weren't seismically designed, because of their inherent ductility and the fact that their top and bottom cover plates had to develop their full axial yield force, they displayed more ductility than the seismically designed pre-Northridge connections. It's a good thing. These are, the black line represents the experimental results. The top 2 figures are for frame FM, the bottom 2 for frame 6M. These are the actuator force versus column drift, and then these two are for the connection moment versus rotation. Now, we tried to post-predict the experimental results in OpenSeas, and we used the modified Ibarra-Crowther model as implemented into OpenSeas by Professor Lignos. And we calibrated the experimental, or the numerical, we calibrated the numerical model quite well to the experimental model. We were able to capture quite well the strength and stiffness degradation. Because of this, we were able to extrapolate these connection behaviors to full frame. So now we had our full frame FM and the full frame 6M models with all the connections with strength degradation parameters in there. So the first step to assessing their seismic behavior, what we did is we performed first mode pushovers. And what you should look at here are these two red lines, the solid and the dotted. This represents the penthouse drift as a function of the base shear force as a function of the total drift at the penthouse. The difference between these two lines is that this one considers P delta effects and the top one doesn't. So they both have strength degradation considerations, but we're not really seeing a global degradation with the one without P delta effects. Therefore, just like the U2 factor suggested, we're experiencing very high P delta effects in this pint-based structure. The next step was to perform nonlinear time history analyses. We used synthetic records from Charette at Cole Poly, originally from Dr. Atkinson. These records represented 2% in 50-year exceedance level. We had 10 records for Montreal, 10 records for Vancouver, and they were scaled by a factor of 1.5 to reflect the importance factor of the MVCC, and we also just wanted stricter criteria for the hospital. And we also decided to go with the 1%, just as a simple pass-fail. We're just looking at inner-story drift levels right now, and we're just going to do a pass-fail performance for this 1% inner-story drift limit. Kind of skipping over some of the intricacies, this is just a little bit of a summary table for the nonlinear time history analyses. Basically what I found was that the frame FM in Montreal was okay. It had a maximum inner-story drift of about 0.9%, but in the other direction it wasn't so hot, it didn't quite meet the limit, so the building still needs to be improved for Montreal. But in Vancouver, in fact, in the one direction, 5 of the 10 ground motions collapsed the frame, and in the other direction, 7 of the 10 ground motions collapsed the frame. Also, it should be noted that for the records that did cause collapse, the records were truncated at 5% inter-story drift limit, and so, in fact, the inter-story drifts that I'm showing here for Vancouver are actually an unconservative representation of the average inter-story drift. So, according to FEMA 356, both frames in Montreal would comply to a life safety performance level, which is, I guess okay, but not for a hospital after an earthquake. And then in Vancouver, technically it's life safety as well, but again, because of this unconservative, truncation of the inter-story drift levels that collapse the frame, it's more of a probable collapse in Vancouver. So clearly retrofits are required in both locations. So the first step to building the retrofits, we need to establish our performance goals. And again, skipping over some details, this is a quick summary of what we were shooting for. So we considered 3 levels of hazard, 2% in 50 years, 1.5 times 2% in 50 years, which was our design level, and then 2 times 2% in 50 years, which was our MCE. And then the second goal was to achieve all of this by using passive supplemental damping without the need for local connection interventions. If you think about this, there's over 100 connections in this building. That would really be a terrible job to fix all of those, and costly. So luckily, Jack will already present it today, so I don't have to go through his whole method, but it's very incredible. Basically what he does is he produces site-specific performance spectra for a given period and relative strength, and he creates these graphs. And what they do is they relate normalized response quantities to various levels of added damping and stiffness parameters for hysteretic, viscous, and viscoelastic damping. It's really quite incredible. An engineer can just look at these and look at all the possible solutions of adding different levels of stiffness and damping, and then jump from different levels of hazard to see how the structure performs. Anyway, so using this, these are the hysteretic damping spectra I used for Montreal. This is a frame FM, frame 6M. He was talking earlier about how your most economical design is on this corner down here, because you get the most normalized displacement reduction with minimal increase in base shear. So those were the theoretical single degree of freedom retrofits that I chose. And it should also be noted that I said that frame F in Montreal didn't need fixing, right? Frame 6M did. we're going into frame 6M, we're retrofitting it. Why not do frame FM? We can get an enhanced objectives performance level in Montreal. So that's what we did. In Vancouver, the frame F, actually we fixed the base first. The pin columns, obviously this was a very large vertical stiffness instability, so we fixed them and then we applied linear viscous damping. For frame FM, it was a pretty good, pretty economical solution. Frame 6M, definitely not. We were really constrained by our performance target to reduce the displacement by quite a bit, and this required very high levels of damping, which will result in a very high increase in base shear, which will require very large damper forces, which we might run into problems in our columns. But let's go with this, run our nonlinear time history analyses, and see how it works. Now, for the hysteretic solution, what we could do is we could use commercially available products like the Scorpion yielding brace, the Scorpion YBS system from Cascanex, based on recent work by Drs. Gray and Kyriakopoulos. What these do is basically they dissipate energy through yielding fingers. It's quite the system. So these are just the model type and brace size that we could use. And then for the Vancouver linear viscous solutions, I love that photo. There's just straight out of their catalog, maximum damper forces and brace sizes required to satisfy my required levels of damping per floor. So in fact, the enhanced objectives were obtained for Montreal after doing the 3-level of hazard nonlinear time history analysis. And in Vancouver, we were extremely close to satisfying the base performance objective. We surpassed the acceleration limit by 0.1 g in 1 story in frame FM, but we're going to say we hit it. Those two figures are for 1.5 times a 2% and 50-year hazard level. This is for frame FM, that's frame 6M. Red represents Montreal, black represents Vancouver. The dashed lines are the original performance for the unitary drift. So in Montreal, we can see that the red lines, the solid ones that is, shifted the unitary drift profile quite a bit. We are well below this 1% drift limit. We are achieving our enhanced objectives for unitary drift. In Vancouver, this is the best part. Look at how much we reduced this unitary drift by. And over here too. And we had no collapses, we had no column yielding, and no column buckling. So we were able to damp out the structure, damp out the response, and create very effective retrofit techniques using this performance vector-based methodology. And there was no, guess and check, trial and error. Like, this is a very straightforward methodology. One thing to consider is, like I said, I didn't look at the foundations at all, so that's something to look into. And yeah, they worked great. So what we learned today was that type 2 construction connections, those that I tested, that is, so only 4 of them, limited sample size, I know, but anyway, they could actually deform at to 2% interstory drift before the onset of strength degradation, and this outperformed most of the pre-Northridge, pre-qualified seismically designed connections. And I also showed that passive supplemental damping is a pretty effective strategy to retrofit this generic type of Canadian structure, and it can be used without the need for local connection interventions. Also, the theoretical single degree of freedom solutions proposed by Jack Guo and Kyriakopoulos, they could be used effectively to retrofit the structure, and we can do all this with commercially available products. And then lastly, limiting the unitary drift of retrofitted type 2 construction frames to below this 2% limit allows you to use simple elastoplastic connection models as opposed to the really intense strength degradation models. So just a couple limitations to my work here. It would be good to test more of these connections, make the results more statistically valid, investigate different types of type 2 connection configurations, investigate the full effect of the steel decking and slab, which was ignored in my experiments, and also to actually yield the connections with gravity loads and then cycle them, because I said that they could deform under gravity loads. Further refine, well, I'll skip 5, he's working on that, he's doing a good job. And then investigate the foundation and the podium components to make sure that they can actually withstand these damping retrofits that I proposed. So, thank you very much for listening, and have a nice day.
I would like to know how you considered the mechanical properties in your steel when you did your visit on the field. And how this, because I probably like the FY or the area is different, phenomenal.
So for the mechanical properties, we assumed that it was all A36 steel, which was a pretty good assumption. Now the ones that I tested, we're trying really hard to get those as close to 250 MPa as we could, but we did coupon tests afterwards, and it turns out that they, even though we were on the fabricator quite a bit, they couldn't actually do that to us. It was closer to about 300.
But you don't have any coupons from?
No, we couldn't. We couldn't.
But
It is the it's in use, so we couldn't really.
We did some coupons from existing buildings, and even though they were for that range, they're usually, the strengths are much higher. The strengths were usually 300, 350, even though based on the code, you have to be looking down below that. So, from the test we did it, back with stronger students.
Guillaume?
While your work is quite incredible, have you think about hybrid retrofit that say using a flag-shaped device, a self-centering device?
You're right. A self-centering device would be ideal, especially for critical infrastructure. However, I was limited by the spectra that Jacko was using, and
that doesn't include self-centering.
it doesn't, not yet. He's expanding it to self-centering devices and viscoelastic plastic devices as well. But he didn't have those at the time when I was doing this,
Okay.
so I was limited to hysteretic and just this and viscoelastic.
Well, it's still expensive devices though.
Professor Limos?
Well, one is a comment, like A36 steel normally hardens a lot, so you would expect something like 1.5 times the nominal strength if you test it. So probably the 300 that he's getting is within the range that that we were talking about before. But I have a question. What were the column sizes that you have?
They were about 14-inch deep, and yeah, the ones I tested were 14-inch deep. The ones I tested in the structure, though, it was a huge range. There was like, well, here, let me just go back to that figure. They were as small as 10-inch.
But what was the flange thickness?
For the flange thickness, I've got, well, this is all imperial, but I've got W14 by 176.
Okay. So when you add this, say the Scorpio,
Yes.
like this will bring a lot of axial force in the column.
Mm-hmm.
Like how do you consider this as part of the model?
What I did is painstakingly I checked every column, the axial load and the moment, and I basically did a verification in Excel to see the interaction ratio. So I checked for column buckling, which is I'm assuming what you're getting at. That's what I checked it that way.
And then the other thing is, okay, I understand the viscous damping part, but again, when you use the Scorpio stiffens.
Yes.
So this means that you may have to, I mean, I would be a little careful with this one because you may have to reconsider the connection issue because you may transfer the failure mode. I mean, it's not just, you add the brace because since you have the stiffening effect, the connection, again, you may have a different failure mode.
Yeah. The thing about that, though, is that in fact, the stiffening is engaged at quite a higher drift limit than the 1% that I have imposed on, especially for the design basis earthquake. For the MCE, my maximum inner-story drift, I believe, is around 1.4% inner-story drift, and that's still that should be within the like the more horizontal portion of the shape that it gives. But it's especially for higher inner-story drifts, so that's a definite concern.
Any other questions for Nick? No? Thank you very much.